You guys, I can't wait to start. So let's not wait until 4:32. So yeah, tell me a bit about you. How's life treating you so far? You're good? I thought on Saturday that the semester is gonna finish at the end of the April. And I realized that you're staying here until May 10. I had no clue. And then I realized that we will finish the lab very early, which means today we're doing lab 9, next Tuesday we do lab 10, and that will be it. And then you will have one extra week to finish the lab report and one extra week for me to finalize the lab report grades. And then we can sit and decide on a final exam day, and we can finish our final exam before May 10. How do you feel about that? I know you're anxious anyway. Right?
Doctor?
Yes.
We have two finals lab on May 7 and May 8.
Yes, I was told, and also your friends advised me, let me open my calendar, they advised me to put the final exam on May 5, because apparently on May 6 you don't have exams, and May 5 is still empty. How do you feel with that? Otherwise, it's gonna be around the same date of your other labs, which is bad. So since we can manage May 5, probably it's a good idea. However, I did not share this with anyone yet. So it's tentative. May 10 is actually, it's like waiting until the last day. You want that card? Seriously? May 10 is a Monday, and we can do that. If you want that, let's do it.
Doctor, I think it's better 10 because we're waiting to know the date of the physics exam. Maybe it's May 4 now.
It is May 4. Or May 10, question mark. Okay, so they told me it's tentative May 4. So بركة طلعت May 5. Is that what you're saying? Because I was planning to give you the exam on May 3 as well. The more we wait, the better, because you know, with your lab reports and me being so slow, it takes time. You see? I'm finishing some classes and some classes not, so yeah, so probably you are my biggest class, probably. Yeah, so I'm gonna keep May 10 in mind. How do you feel if we talk with the others about May 10? Would you want our final exam to be the last day of the semester? May 10 is a Monday. Yeah, so May 10, yeah, other than Carl and... Okay, so much better than May 5? It's gonna be somewhere around evening though, or anytime you finish your classes, because I don't have classes in the afternoon, but your class, like the other section. Probably around 5 p.m. Do you have classes Mondays around 5 p.m.? The last day, probably you're gonna be free from other classes. Anyway, probably I can ask you this question again next time I see you. Now back to Kausar. Kausar had a very important question in Lab 8. And everyone else, if you have questions related to Lab 8, we can do this now. Yes, Kausar, please speak up.
Hello, doctor.
Hello. Just call me Jessie. It's the end of the semester.
I have a question regarding the report, the questions inside the report and not actually the PowerPoint.
Okay.
The last question, when we asked us to compare with item 1 and item 3, what are we supposed to actually say or do or calculate?
Number 3, compare.
Number 7.
Okay. From the slope, find the velocity. All right. So
yes,
you found the velocity from the slope. However, you already found the velocity
yes, at each sequence.
Here as well, right? Because you already have V, and you found the average. So you found V using two different methods. The first method is by moving the piston, And the second method, which is here, that is by moving the microphone. So you found the velocity twice using two different experimental methods. So you can compare them. It's not really item 1 and item 3, it's item 7 and item 3.
And also in the first question, we calculated the velocity using the temperature.
So basically they wanted you to compare what you found with the original one. Compare with both 1 and 3. So you compare the answer of 7 with 1 and the answer of 7 with 3. Yes, you're totally right. I missed number 1.
And do I take the one that I calculated as from the temperature as the theoretical one, or no?
It sounds as such because you're using an equation. So it's like you're assessing how good the equation is. Because in item 3, you used experimental technique to find lambda and therefore find the V. And then the slope is experimental. We can assume that the equation is the one that is the most theoretical. But if you really think about it, all of these are using equations and using measurements as well. Didn't you measure the temperature using the thermometer?
Yeah. I used the temperature that you put in the slides, which is 18.
Yeah.
It's a point with akid uncertainties.
Yes, of course. Yeah. All right. What
so
else?
There's no percent difference or anything. I just compare them and say.
No, compare means find the percentage difference. You cannot say close or big or smaller. No.
So I will take the one which is in item 1 as the theoretical one. I will say
that.
it's the most appropriate one to take.
I would do that. I wouldn't call it theoretical. I always like to call it reference, as my reference.
Okay. Dear, I will take it as my reference.
Yes.
Thank you.
That's it?
Yes.
George, go ahead.
That's in question 6. Do we need to find the error on the slope?
They don't say. They actually plot. Okay, they don't say the slope, but in number 7, they say from the slope. Like in number 7, you calculate the slope, and no, it's not required. If you want to do it to be able to round your slope, you can do it as extra, because you know what you have in the lab report is like the minimum requirement, and the lab report is a template. So you are more than welcome to do anything you want. But what is in the lab report is the minimum requirement, especially if you're using the linest function and it takes you a second. Why not do it to round your value, you know? But if it's time consuming, please don't do extra work if you believe it's taking a lot of time. Sometimes you lose the point after you do so much work. So the lab report is a template. It's short because we want it to be focused. So we need it to stay focused, and at the same time you can do extra when needed and if needed, but don't do a lot and lose the point. So I don't see that they want it. So if you want, don't do it. More questions related to lab 8? Yes, Maria.
Doctor, I took the temperature as 25 degrees. Is that okay?
So because you couldn't find our actual temperature?
No, I took room temperature as 25.
Where is it 25? I'm sure at home, at your house, it's even colder. Actually, it will probably it's gonna be a lot different than the experimental ones, because when we did the results, we had a different temperature. So I can tell you can keep it, but how about the fact that you will have a lot of, like, your value will look so not accurate eventually. V of the sound experimental will be so much different. So it's obviously wrong to keep it. And since it's not going to affect your lab reports, you can simply just modify item 1. You're going to be all right. So I say follow the measurements given to you. Okay? And if I'm not mistaken, the measurements are here in this section in the PowerPoint, and which means that is it 18? I can't remember. Yes, 18 degrees. 18 degrees with 1 decimal, if I'm not wrong, if you look at the smallest subdivision divided by 2, the uncertainty, I mean.
Okay, doctor, thank you.
Okay, you sound disappointed. I'm so sorry. Yeah. What else? Anyone? Questions? Lab 8. We're good? Okay, fair enough. If I know probably you're not done doing lab 8. So, but no uncertainties are required, right? I think only when you do the average, you want to find the RMS. I don't know, Kausar. Read the question. I don't want to answer your question. I want you to think about it, okay? For question, if they don't say, don't do. If you want to do something extra for the sake of rounding your values and making sense out of them, and it's not time consuming, do the extra, okay? Let's keep it like open-ended. So it's up to you. And the questions are clear. If they don't say it, it's obviously they don't need it unless you need it personally. Okay. So yeah, I was saying that if you still have questions for lab 8 and you want to ask later, we can answer your question anytime you want. So it's not now or never. We can talk this evening, tomorrow, anytime you want. Now lab 9, this is the first lab we're doing in the section related to heat. Linear expansion, obviously when we heat a certain solid, it's gonna get longer. So that's why we say linear expansion. Lab number 10 is also related to heat. It's the specific heat capacity of some solids as well. So these are two experiments under the big title heat. This is the outline I would want to follow. What is linear expansion? How do we calculate or measure the coefficient of linear expansion? The setup, the lab report, and how can we discuss the coefficient of volume expansion? The physics is very easy. The experiment is very easy. The lab report and the setup, very easy to understand. The lab report is very short, and you're gonna see it's gonna be really quick. What is linear expansion? Just tell me anything you can think of. Linear expansion, and I'm all ears. Yes, linear expansion. Who's expanding? How? Why? Due to what? And why? Yes? What is linear expansion? Anything you can think of, even if it's wrong. Have you ever heard of this term, linear expansion? All right, so it could be due to a temperature change. Why not? Anything else? Expansion means increase in something. Okay, so expansion equals increase in obviously length, because it's a linear expansion, so it's probably in size or size. Okay, what else? So it probably would be increase in volume as well, question mark, in volume. What else? It's due to what? And who undergoes linear expansion? A certain object, all objects, solids only. So it's due to heat, and you said related to some coefficient, related to a certain coefficient, and then you said at a certain rate, and by rate we mean change of something over change in time. So is any time component, is that what you're trying to say? So rate means how fast it's increasing, and fast means time component. Is there any time component? What else? Solids only. So steel expands, and some people are saying solids only. Solids only. What do you think? What else? Most probably metals only. So for example, wood will not undergo linear expansion, probably. Good questions. Ya Allah, your class always delivers the best interaction. I don't know why. Probably you're too many, or you're simply active. What else? Linear expansion. Any application? Anything around you at home that undergoes linear expansion and you have issues? It bothers you probably? Train stations. What do you know, Ali, about train stations? Exactly. So it would affect train stations, and they're actually made of a certain metal, steel or not, I don't know, it depends. And basically, you can have issues and problems if the rails actually change in length. They will get dislocated probably. Yeah. All right. If you can think of something else, let me know. So basically, my first example was the rails. And you can see that you can have an issue because of that. So you will have rail buckling. In other words, they will dislocate because of that, and it could be an issue. And this is an example where we can solve this problem due to the thermal expansion of the joints. So in this bridge, they used special joints to have an easy and safe expansion between seasons without having buckling and without having dislocation of the bridge. So, and you know, in certain countries, the temperature change could be up to 40 degrees, especially, you know, and if you're far away from the ocean or from the seas, the temperature can go from plus 20 degrees down to negative 20 degrees. So we're talking about a big change in temperature. So this could be an issue. Now, how do we measure or calculate the coefficient of linear expansion? It's a very simple definition. It's related to the change in length over the length. So this is the relative, let me get a pen. So this is the relative increase in length, which means it's the delta L over L, and it's related to temperature, and no, Romy, it has nothing to do with the time component. Okay, so it's the change in length over length, and then you divide by the change in temperature. You see? So in other words, I'm not saying that some metals can expand faster or slower. It's only how much they're gonna increase in length over a certain increase in temperature. Okay, so you can do the experiment, heat a certain object, measure the change in temperature, measure the change in length, measure the initial length, and that's it. So it's experimentally very easy to perform. This table, I shared with you this table for many reasons. I wanted you to see three things. A bit the order of magnitude, but before doing that, can you tell me a bit what could be the unit for alpha, the coefficient? From the equation, you can guess easily. What is the unit for alpha? I bet Ali is going to answer this because Ali is fast with units, or am I wrong? So what is the unit for alpha if you look at the equation? Easy. All right, some people would say no unit. That's an answer. Any other answer? God, did you say second to the minus one? We don't have temperature and we don't have time component. Did you confuse time with temperature? Probably. Probably means you're not sure. So what could be the unit for alpha? So far, the answer that is no unit is wrong. The answer that is second to the minus one is wrong. 1 over degree Celsius, Christopher, is true. So probably this is what Carl was confused about. So the unit for alpha is the inverse of the degree Celsius. Also, it could be the inverse of the Kelvin, because remember, the jump in temperature, Kelvin or degree C, is equivalent. You know this, right? Because the jump is the same for Kelvin or degree C, not the temperature itself. So by saying the same value in 1 over Kelvin, you can keep the same value, no need to convert. All right, what I want you to notice from the table is one thing, that is the order of the magnitude. Can you name a solid that has a big coefficient of linear expansion? In other words, this solid expands a lot due to an increase in temperature. Which one will you pick? So which solid increases a lot due to the in size due to the change in temperature? Any answer? Aluminum increases a lot, lead increases a lot. Yes, that's so true. And can you name an object, a solid that you can find around you that is barely affected by temperature, or it has the smallest or one of the smallest coefficient of linear expansion? Let me see where steel is. Actually, steel is an alloy, isn't it? Oh, it's here, iron or steel. They're very close. Yeah. So the question is, we want the least. Quartz. Yeah, anything you have around the house? I would think of glass. I would think of marble, because you know you have glass and marble at home, right? Pyrex, is there Pyrex in here? Yes, glass Pyrex, exactly. All right, so they don't expand a lot. They do, but not a lot. So this is the one thing I wanted you to notice. Another thing I wanted you to notice is that the coefficient is temperature dependent, and that's mind-blowing and confusing at the same time. How come alpha changes with the temperature? Isn't alpha the coefficient that will tell me how the length changes with temperature? So how come I have alpha for 20 degrees C and some different alpha for a different temperature? Keep that in mind, think about it, and we can talk about it later on probably. But yeah, and also I found somewhere that alpha changes with temperature, yes, but slightly. So it's not a big change, all right? So those measurements were done at 20 degrees C, and go figure what they mean. Think about it and tell me later. The third thing I wanted you to notice is that you have the coefficient of linear expansion and the coefficient of volume expansion. We call it beta, and the unit is still the same, by the way. And you can compare both values and probably come up with a theory for later on. I'm not going to discuss it now with you in class, because some of the questions in the lab report are related to this, okay? So keep it in mind. Now the setup, what do we have? Very nice, very easy to handle. You have a steam generator. The steam generator is an actual container, and you have a machine that would heat up whatever liquid you have inside the container. I will open it and we'll fill it with tap water. I want to collect steam by boiling water. You see the on-off button. You see you can increase the power from 0 to 9. So for you not to wait a lot. And this is a tiny lamp, a LED that shows you that the thing is on or off. You connect it to the mains, a regular plug, and it has you close it tightly, and the lid has two openings for you, and steam is gonna escape from both openings. You can use a tube to collect the steam from the first opening. If you want to close the second opening, you can easily use a tube and clamp the tube to close it. And this is what I'm gonna do, because I only want to collect the steam from one tube. I will collect the steam from this tube and connect the tube to one of the rods. Okay, the rod is empty inside, so I'm gonna have steam inside the rod. Steam is at a very high temperature. The rod is gonna heat up, and it's going to increase in length. I have 3 rods, 1, 2, 3. The white one is aluminum. It's very light and it's very whitish, you know, it's aluminum. The red one is copper. I can guess from the color because red is always copper. The yellow one is usually brass or tin. In your case, it's gonna be brass because according to the manual, I have brass, copper, and aluminum. 80 centimeter is the approximate length. And the results, do I have the results open? I have them here. Let me open the results, and you can take a screenshot if you don't want to wait for me to provide you in the evening. The length is not 8 centimeters. شو هيدا 64 centimeters? 80 centimeters versus 64. So probably the 80 centimeters is not related to those rods. However, the rods that I have in the video are very close. All right, so probably when we measure with a ruler, the measurement is more precise. Yeah, or probably these results are related to the other setup that I have that is also Pasco, same manufacturer, but they're a little bit different. But let's follow the results given to you, okay? Because the R and the delta L are related to those rods and not the ones we have in the video that are basically very close. What else? You have this tube. I'm gonna use this tube to collect the steam, and yeah. I'm gonna use this dial gauge that would give me the increase in the length, because the length I can measure it with a regular ruler, but the increase in the length cannot be measured with a regular ruler because I'm measuring something around 1 millimeter, a bit less, a bit more. And you know, a regular ruler cannot measure this easily. The dial gauge can give you more decimals, it's more precise, it's more sensitive. So you're gonna put the dial gauge on this ring. I don't know if you can see the white ring. And whenever the white ring is gonna move a bit, the dial gauge that has a leg here is gonna measure directly any change in length. We also have this foam holder. It has three reasons to be there. One reason is for you to hold the rod, the very hot rod, without burning your skin. Second reason is under this foam holder, you have a thermistor, and we want the thermistor to be isolated. The job of the thermistor, by the way, it's a resistor, the resistance of which will change when the temperature of it will change. So if you put the thermistor in an environment of 20 degrees C, it's going to give you a certain resistance. If you put it in an environment that is hotter, it's going to give you a resistance that is different. And we have a chart that would give you for each resistance the temperature. So it's a very good way to measure the temperature of solids, because you cannot use a regular thermometer to measure the temperature of a solid. Usually we can use a thermometer to measure the temperature of the surrounding air. We can use a thermometer to measure the temperature of a liquid, but you cannot touch a thermometer, put it in contact with a solid to measure the temperature of a solid. You need a thermistor to be able to do that. And thermistors actually give you a digital measurement. You know, when you have digital thermometers, they're actually thermistor based. They're not based on mercury, neither alcohol, you know. So thermistors are used everywhere, and you're gonna see how it works. Also, you can use this foam holder to keep your thermistor safe, because trust me, it's not user friendly. You're gonna touch it and probably the wire is gonna break or something, because the equipment we had in the past that are very similar, and Pasco as well, we ruined, and I ruined one by simply holding the thermistors and moving them right and left, plugging them in and on. You can easily destroy the wires. So I'm glad now our thermistors are safe inside. All right, this is another picture of the setup. You can see the tube. One of the tube is clamped just to close it, and another tube collects the steam. It will go into the rod, and here you have the dial gauge attached to the rod, measuring any increment or increase in length. This is a multimeter to measure the resistance of the thermistor. The thermistor is connected to this plug. So this is the wire of the thermistor. I don't know if you see it. And then you can measure easily. This is 10.66 kilo ohms, and I will show you the chart in a moment. This is a close-up of the dial gauge. You can see a certain measurement. You can click inch millimeters. You can click the on-off button. You can zero it. Basically, you simply have to put it, make the setup ready, and then zero to measure any increase in length, because you don't want any random measurement. What else? This is another picture of the setup again, and this is the chart. You can see for every value of the resistance, you have a different temperature. You can observe if that's a linear increase or not, but who cares? If you get any value or any value between those values, you can guess. So think about the smallest jump in temperature. So you can call it smallest subdivision divided by 2. So you can give up to 1 decimal, don't give more. And those values are in the thousands. That's why we have 10.66 kilo ohms in here. And this is not enough because it goes up to 45 degrees, and you would go up to 100 degrees as well. So in the results section, I gave you both charts from Pasco. So this is exactly what I have on my desk. You can see it in the video. So you will reach a resistance down to 680, which is 100 degrees C. This is the temperature of steam, I suppose, as soon as you have boiling. Yeah, and probably you're gonna reach this or a little bit lower. Yes, this is a screenshot from the video to show you the chart. The chart is, you have it on both sides of the paper. So you have up to 45 and then from 46 up to 100, but it's not visible. That's why I got you the original chart. This is the table of measurements. You need to take copper, brass, and aluminum. Unfortunately, I have results. Where are the results here? I have results only for brass and steel. Aluminum, I did not take the results because I remember back in the past when we were in the lab, I asked the students to do 3 trials. I thought 3 trials would give more accurate results, more precise results, because you can find the average. And since the experiment is time consuming because you need to wait for the water to boil and then wait for the rod to heat up to a certain temperature that is constant, it's time consuming. So it's like you're repeating the thing 6 times, and you need to wait for the brass rod to cool down to do the experiment. That's more waiting. So I thought probably not to ask the students to do it for the 3 rods because it's gonna be really long. And probably because we had so many benches and not so many rods, I thought we can share rods, like some students did aluminum and steel, some did brass and steel. However, I only have measurements for brass and steel, okay? So you can simply remove the extra row if you want. This is the length initially, before you do the experiment. This is the delta L, the increment, the increase in length. This is the resistance at room temperature, from which you can find the temperature. This is the resistance that is hot when you wait enough for it to heat and to reach a constant value. This is where the experiment stops, whenever it reaches a constant value. You can find T hot, and you can find delta T by finding the difference between T room temperature and T hot. And definitely use the values in the table to find alpha, the coefficient. And then they're gonna ask you questions about volume expansion. Just keep in mind that volume expansion occurs because each side is gonna increase in length, each side is gonna increase in length, and each side is gonna increase in length. That's why the whole size is gonna increase in volume. And they will ask you to speculate about the volume expansion and probably find beta out of alpha. It's not tough. Think about it a bit. Probably you can read about it a bit and come up with a theory. Okay? And I'm not going to give you more hints. Okay? Just keep in mind that volume expansion happens because of linear expansion, and volume is 3-dimensional. So you will have linear expansion on 3 dimensions and so on. Okay? Probably you can find volume from the length and guess what is the coefficient. Think about it, it's not tough. And that's it for the experiment. I had a small extension related to water. Some interesting facts about water. As you can see, it's not in the outline because it's not related to our experiment. It is related, but it's not relevant for the lab report. So you tell me, any facts you know about water? Do you think water expands or contract when you heat it? Any thoughts? And I mean by water in any state, solid, liquid, or gas. All right, when it evaporates, what happens to the steam, to the water vapor? It expands, yes, definitely. So far, Roy and Carl are stating that water in the gaseous state will expand when heated. PV equals nRT will tell you as you increase the temperature at a constant pressure, the volume increases. I'm talking about ideal gases. And yes, why not? It's gonna expand, obviously. And this can be explained if you go down to the microscopic level of temperature related to the speed of the microparticles. So definitely. What about the liquid? Yeah, kinetic energy. What about the liquid state? What about the solid state? What happens? Water itself, and I mean by water H2O, it shows some exceptions. Have you ever heard of those exceptions? What happens when you cool it down? Does it really contract? And what happens when you cool it down even more and more? What happens? Does it keep on contracting? So Ali's saying solid H2O is less dense than liquid H2O. So does it expand or contract? Emilio's saying Water expands when changing from water to solid. So Emilio is saying it contracts. No, it expands. Liquid is denser than the solid. H2O molecules come closer together when, Jana? In which case? When you heat up or when cooling, it contracts? Can you give me a random example to explain where in your daily life you saw this? Because some answers are confusing. So in your daily life, ice. Yeah, tell me, Roy, about ice. Unmute yourself. What happens? Very simple. You know this when you were a toddler. You know, my kids, the young ones know this. What happens when water turns into ice?
The water particles will get closer to each other, so it becomes a solid.
Okay, and
freezes.
assuming that the water particles come closer, the solid state is smaller in size?
Yes.
So when you put water in a container and you freeze it, the solid is gonna be smaller?
No, it takes the volume available in the container.
And if there's no more available, so does it decrease or increase in size? So you're saying
I think it stays the same.
Okay, so I know I'm confusing you and I love this. Confusing you is the first step to understand what's happening. So sometimes you say increase, sometimes you say contract. So very simple. When you have water and it becomes ice, it overflows, it takes more space. And this is contradictory to the general theory. And that's why we're stating that water, H2O, creates a certain exception, right? And can you tell me now, for the students who already told me that the molecules get closer, do they really get closer? Romy said molecules come closer, and somebody else, Jana, said molecules come closer. Do they really come closer for H2O? Probably they get farther, and that's weird. Yes, it's actually due to the hydrogen bonding between H2O and H2O, and you can see it in this picture. So water molecules are not too close. However, solid molecules are even farther, and it only works for H2O particles because of the hydrogen bonding, which means water creates an exceptional behavior beyond 4 degrees C. And to be honest, I discovered that really late. I was 23 or 22 years old. Like I was really old. And I was like, really? Water behaves as such? This is really awesome. If we need to talk about density, and Ali discussed the density at first, water is denser at 4 degrees C, which means it creates this, it has the smaller volume. If you heat it up, it's gonna expand in size. And if you cool it down, it's gonna expand in size as well. Isn't that weird? At 4 degrees C, it's the smallest in size and the denser. By the way, that's why an ice cube floats on water. All other solid states of other material, of other, what do you call it? Liquids, they actually sink. Only water, H2O, the solid phase of water will actually float. And this is the exception. Next time you're gonna drink a liquid and you look at the ice cube and you see it's floating, think that all other liquids, when you turn them into solid, they actually sink and they don't float. Only when heated from 4 degrees. Yes, 4 and above, you have expansion. 4 and below, you also have expansion. You see? Yes, it's gonna expand. And if you have a container full with water, I used to hear, don't make it so full, because when it goes to solid, it's gonna expand even more. Probably the container can explode or it's gonna overflow. From 10 to 4, yes, there's contraction, which is regular for all solid, for all liquids. Like if I'm talking about any oil, from 10 to 4, it's gonna contract. From 10 to above, it's gonna expand. So the behavior is very, why 4? Yes, because at 4, probably this is what breaks or not. This is where the hydrogen bonding starts forming. you know? So it has to be related to hydrogen bonding. At 4 degrees C, this is where probably they're gonna start happening, and this is where the molecules are gonna start pushing farther apart. Yes, the least volume, exactly. So let's write it here, the least volume, least volume. Okay, yes. And one application of this is how the behavior of the water flow in a pond on a different season. Didn't we say that 4 degrees C is the denser part of a liquid, of a water, which means in the hot season, the water temperature is gonna be distributed as such, which makes sense because the deeper you go, the colder the water is. 4 degrees C is gonna be at the bottom of the lake. Whenever you are in the cold season and you have ice on top of the lake, you're gonna have zero, and then it's gonna heat up as you go down, and not the opposite, because 4 degrees C is denser and it's gonna go down, you know? And this is gonna affect the water flow, and it's gonna affect who's living in the pond. I mean, animals and plants. So it's gonna affect the whole ecosystem. Yeah, so it has a lot of consequences on nature, water, and weird facts about water. Okay, we're not going to discuss specific heat capacity of water that I also believe is very interesting. Probably we can do that next week when we have lab 10, specific heat capacity of water, and how it has very interesting consequences on everything around us, and most importantly the environment and probably the human body, right? So interesting facts about water is not relevant for the experiment, but I thought since it has a weird behavior with expansion or not, probably talk about it a bit just for fun. So that's it for our experiment. Please let me know if you have questions. Otherwise, I can stop recording, and